So our goal for this instructional video is this question: how do I help my students understand the meanings of the operations? So that's where we're headed with this instructional video. There are basically four big ideas. Number one, that addition and subtraction are connected. And in fact, when we teach addition strategies, it kind of wraps up the subtraction strategies as well. We also teach through the big ideas that multiplication involves counting groups of the same size and then determining how many are in all. We also need to stress that multiplication and division are related and that models can be used to help solve those problems. It actually helps students really understand the concepts behind the problems when models are used. And models can be manipulatives, like something they can hold in their hand, or they can actually draw models. So your book pointed out some addition structures. We have the join problems, which is the change is being added to the initial. Now, that's really something that we're a little more familiar with, the change being added to the initial. And a sample problem will be something like Sandra had 8 pennies. George gave her 4 more. How many pennies does Sandra have altogether? So we know that Sandra had the 8 pennies, that was initial. George gave her the 4 more, that was the change, and then the result. So now we go on to the separate problems, and this can be very confusing because it actually reminds me a lot of subtraction, and that's where the addition and subtraction are related. So the change is being removed from the initial, and what is the result? So a sample problem would be Sandra had 12 pennies. She gave 4 pennies to George. How many pennies does Sandra have now? But using the addition strategies, knowing that she had 4, she's giving 4 away, and that we know that 8 plus 4 equals 12, we know that that result would be 8. And then there's the part-part whole. In the part-part whole, we know that there's 2 separate parts, equal or not, and either the whole is missing or one of the parts is missing. So for this one, for example, the whole is unknown. George has 4 pennies and 8 nickels. How many coins does he have? So we would know that we would put the part of 4 and the part of 8 together to get the whole. Or we could have a part missing, and again, this reminds me of subtraction. So you have to think how addition and subtraction are related. George has 12 coins, that's the whole. 8 of his coins are pennies, and the rest are nickels. How many nickels does George have? And again, knowing that the parts 8 and 4 make 12 would help us to understand that problem. Now we go on to the actual subtraction structure, which is basically comparison problems. And there are 3 ways to represent them. So we look at which quantity is unknown, either the smaller number, the larger number, or the difference. So if the difference is unknown, we could still stick with George and Sandra here. George has 12 pennies, Sandra has 8 pennies. How many more pennies does George have than Sandra? Or how many fewer pennies, we could say. So that is a way to describe the subtraction structure. Now we move on to multiplication and division problem structures. Now, those particular ones, you have to think equal groups, okay? So our scenario here is Marge has 3 bags of peaches, 6 peaches in each bag. How many peaches does she have altogether? So we can see that we can put 3 separate groups, 6 peaches in each group, and then put them together, counting them, either adding them, or that 3 times 6 equals 18. Now, we could also do where a whole is unknown. in fact, like this. Mark has 4 bags of apples. There are 6 apples in each bag. How many apples does Mark have altogether? Now again, the student can use repeated addition in order to get that. And there are several other examples that your book gave. Now a comparison problem could be something like this. Marge picked 24 peaches. She picked 6 times as many as Lynn. How many peaches did Lynn pick? And again, we're looking for that particular piece that is unknown. And in this case, it is a kind of a partial that's unknown. We want to know, because we know that 6 times 4 is 24. But we know that, the children do not. So we know that we're looking actually for a factor there. So to teach addition and subtraction, I suggest using a lot of hands-on activities. Your book had several pictures, and I just copied a picture from there. But you can use the part-part whole, like in A or B, which shows the part-part whole. You can use the joining method, which is kind of like a part-part whole if you're looking at the picture to the right. Counters, this is really interesting because you match, and then what's left over is your answer if you're doing subtraction. Cubes can show the same thing, can show the difference. And number lines can show the same thing. So look at the bottom picture of the number lines. You could actually start with, like, there are a total of 8 coins. Sandra has, it looks like that is 5. Sandra has 5. How many does George have? So we have the overarching number of 8, that little arch drawn there. We know that Sandra has 5. Now how many jumps does it take to get to that 8 from 5? And that would leave us with 3. So those are ways to use models and drawings. In multiplication and addition, it's important that we use real-world problems. We don't want to use problems that are meaningless. So we want to basically create things that children are interested in and that have meaning to them. Now, one of the interesting things when teaching division that kids have a hard time sometimes understanding is what to do with the remainder. So do we throw it away, or do we force the answer up to a higher number? Do we round? So we just can't think of problems as remainder 3. One of my favorite problems has to do, that I told my class several years, has to do with a field trip. And I said, you know, we have to take minivans, and there are 26 of you, and 5, I think I said 5 people can fit in a minivan. So how many minivans are we going to need? Well, they divided and they came up with 5 remainder 1. And I said, well, we can't have remainder 1, so who's going to choose not to go on the trip if we only need 5 vans? Oh, we need 6 vans, who's got to take that other person? So having them think about, do we force the answer up to a higher number, or do we just discard it? Like, I have a ribbon that is, I don't know, 24 inches long, and I want to make bows out of that ribbon. And each bow is going to be 7 inches long. How many bows can I make? Well, the answer then would be 3. And so I'm just going to discard that remainder of those extra 3 inches I have with my ribbon. So the students need to know the context of the problem in order to decide what to do with their numbers at the end. So here are some examples for model-based problems, what you can do for multiplication and division, and it all has to do with equal sets. Arrays are very interesting because it reminds me of finding the area of something. So if the area is, 6 foot times 12 feet, then you know that that is 60. But here you can actually do multiplication facts using arrays and number lines. If you look at the number line to the right, down below in the bottom right square, it's how many 4s, 4 times what equals 20. So it's how many jumps did we do of 4, and it's 5 jumps. So these kinds of things help children understand the concept behind addition, subtraction, multiplication, and division. So they're not just performing an algorithm, but they're actually understanding the meaning behind those. Now you have properties for multiplication and division, and many of you are familiar with them. Commutative, if you have two numbers in a multiplication problem, they can be flipped either way. So here's an example, an array can show that. The associative property, you can use parentheses, and you can flip those parentheses any way you want. Again, you can use something like an array in order to show that. Then you have more properties, the 0 and the identity property. For multiply anything times 0, it's 0. Multiply anything times 1, it's the other number, so that's the identity property. And then your distributive property, where you can take larger numbers and actually break them apart and come up with the answer. This type of property, distributive property, really helps with mental math. So let's take the green box down at the bottom where you can see 5 times 7. Let's say a child really has trouble with their 7s and for some reason they don't think of 5s. So instead of doing 5 times 7, we break up that 5 into 3 plus 2. So 3 times 7 plus 2 times 7 would equal the same thing. So 3 times 7 is 21. 2 times 7 is 14, and if you add those, you're going to get 35, which is 5 times 7. So it works either way. Now, with context problems, as you're writing word problems, you need to really help students focus on the meaning of the answer instead of the numbers. Many children just want to jump in and pull out the numbers, and they don't really understand what is happening in the problem. So second, we want to put a focus on the structure of the problem by identifying the numbers that are important, or if there's any information we don't need. So first, the meaning of the problem, what's happening. Visualizing or drawing a picture can be very helpful. And then what numbers do I need? What don't I need? And then thinking leads to a rough estimate of the answer. Will it be a small number? Will it be a large number? How many will it be? And if we think through those things, like I once had a problem that I did with students having to do with a flagpole, and one of the answers of the flagpole, was that it was 15 miles high, and the student chose that. And I'm like, have you ever seen a flagpole that's 15 miles? It's that reasonableness that we want them to think about. That's why a rough estimate is so important. So hopefully what we just discussed will help you to understand how to help your students understand the meanings of the operations. I encourage you to watch the 2 videos that are included under Chapter 9 of this actually in action in classrooms.